Let's talk about understanding and comparing distributions. Remember, a distribution is how are things spread across a number line. So this is how something is distributed. Now, when we want to understand it, we can talk about the mean, the median, the mode, the range, the standard deviation, the IQR, different values to give it context, which all data needs. And to compare it, we would compare it to another distribution down here, which might have a different center, might have a different spread. We need to know which ones we should use, which centers and spread, and how to talk about these distributions to understand and compare them between groups. So let's say we have some wind speeds at the Hopkins forest right here collected between different seasons. Well, looking at this data right here, we'll move it down just a little bit. But you have this data set, and what is the shape, the center, the spread? Remember, shape determines center and spread. So the shape of this data is unimodal, right skew. Draw your monster man. Right to the high, left to the low, whatever way the monster man's tail goes. That's our saying to remember the high side, the larger numbers, is going to indicate to us that this is right or positive skew. Now, because of this being right or positive skew, we would choose the center as the median and the spread as the IQR. And those numbers are reported right here. The Q3 and Q1 are given, so we need to take Q3 minus Q1 to find the IQR, and that's going to be 18, I think it is. So it looks to be 1.82, and that's found by doing 2.28 minus 0.46 right there, double checking it right there. That looks to be correct right there. 1.82 is the range of the middle 50%. Remember, the IQR is the range interquarters, range of the inner quarters, and the 50th percentile would be 50% of wind speeds are at or below 1.12, or 50% of wind speeds are at or above 1.12. And so we don't want to just do this with one distribution. We want to do this with multiple distributions. Notice that this one actually probably has a higher standard deviation, which we won't use because it's skewed, but it's more spread out. It would have a different IQR then. This one right here is more right skew. It's hard to say. That one is more uniform, more flat, but it does have this weird tail at the end, and it does look more spread out along the number line. So because of that, it would be more spread out. The other one's more clumped together. We could find the exact standard deviations, or we could look at the values right here. And here is the standard deviation of winter. And yes, I was right. Winter has a larger standard deviation because it's more spread out. Once again, think about butter on your toast, the way I like to describe it. If this first one was spread out like this on your toast, there's the first one. The second one would spread it out a little bit more across the toast. There's the second one spread out a little bit more across the toast. So the uniform actually is more spread out in this instance. And it has a higher standard deviation. It also has a larger IQR, which is how we're going to preferably measure the spread right here. So we would compare these two distributions on their spread based on IQR, and we would talk about the spread that way. And the proper measure of center is going to be the median. So the wind speeds are typically higher during the winter, and they have more variation. So think about what we've learned from this. Wind speeds are typically higher during the fall/winter, and higher by typical we mean the median, because this is right skew data. And the IQR is going to show us that they have more variation. The middle 50% is more spread out for the winter wind speeds based on IQR being 50%-ish larger than the summer IQR. So when we make histograms, we oftentimes like to make stacked histograms if there's multiple groups. Now be careful though. Whenever you do stacked histograms, where one histogram is stacked on another, you must make sure to give them the same horizontal scale. It might look to you that machine 1 has a higher distribution than machine 2. But if you put them on the same scale, you'll notice machine 1 is much lower than machine 2. Take a look at the disparity in the number lines here, where they're very not the same. And you'll notice that you're not comparing things equally. Usually you want to make the count axes the same, but the number one thing is a common horizontal scale to evenly compare these and see where the differences are at. And now we get into the 5-number summary. The 5-number summary is easily remembered by drawing 4 quarters. Draw 4 quarters and label them quarters. With this, put your lines down on all sides of them. Now that we have lines on all sides of our numbers, we'll make this a tiny bit smaller so I have a little more room. There we go, nice and neat. Bring this over here. Watch this. How much data have you gone through at the very start of your data set? 0%. Now you've gone through 25, 50, 75%, 100% of your data. Now let's try to come up with some names we've heard of before. The lowest number in your data set would be the min. The highest number in your data set would be the max. Now, think about this. 25% of your data, Q1. 75% of your data, Q3. And this can be called Q2, but more commonly, the 50th percentile is called the median. I like to draw my 4 quarters right there, and then you can think about what the IQR is. The IQR is the range of the middle 50% found by Q3 minus Q1, and you can subtract those numbers right there and find the range of the middle 50%. So for this data set, we would just take these numbers right here, subtract them, and once again, we did this earlier on to get 1 point, and then I think it should be 1.82. Could check my math earlier, but 1.82 subtracting 2.28 minus 0.46 right there to get the range of the middle 50%. And there are values in these positions, but the percentiles on the bottom represent what percent of the data we've gone through, the nth percentile, the 75th, the 50th percentile, which represents the median. Hopefully this helps you better understand that the IQR is the range of the middle 50%. It can be found by Q3 minus Q1, and the remaining values here are known as the 5-number summary. Draw your 4 quarters, put your lines down, and try to remember this is a good way of practicing right here to memorize the 5-number summary. Here's what the data looks like, and usually we want to use this for skewed data. So notice how this is right skewed data. We always draw our monster man when we remember. And right to the high, left to the low, whatever way the monster man's tail goes, positive, high, right skewed data. So there we go with that. And with this in mind, you'll notice that the numbers here are further away. Now, between each of these is 25% of the data. From the max to Q3 is 25%, and from the Q3 to the median is 25%, from the Q1 to median is 25%, and Q1 to min is 25%. Notice how the disparities between these numbers are larger up here and smaller down here, and that's indicative of right skew data because you're pulling out the higher side of the data to where you might have data clumped up here, data clumped up here, data clumped up here, and then data clumped up there in the top 25% of the data. They're not perfectly circular shape because the data gets more spread out as you go to the higher side of the data. Those are our quarters down below if you can't tell. And so how do we visualize this? A box plot is going to be a visualization of the 5-number summary. So once again, box plots are going to be a way to visualize univariate quantitative data. We had a few ways already. We had histograms. Histograms look like the following. We had stem and leaf. Put a stem and leaf right here. And a stem and leaf is going to look like where you have the numbers, and then you have the stems rather, and then the numbers over here in the leaves. A dot plot right here is going to have the dots, and they just show you how many observations are in each one. So there'd be a number line right here going from like 0 to 100, and then this would also be like from 80 to 90 because it's a quantitative distribution. And with this in mind, box plots are unique because they're a much smaller, compact way of doing things a lot of times, and you can see the 5-number summary. So let's start making one. To make a box plot, the first thing you need to do is draw your box. The box is going to be Q3 to Q1. There it is. There's the box. The next thing you need to do is mark the median in the middle of the box. Now, it's not going to be in the middle. I said middle, but it'll be there somewhere, and technically the median could be on the very bottom. Sometimes Q1 overlaps the median, so wherever the median is, numerically speaking, put that dash. A lot of times it'll be towards the middle-ish, especially if the distribution's more symmetric, but make sure to find where the median is and put a dash. If they do overlap, sometimes you'll see a box plot where they make the one a little thicker, where the median is at, to let you know that the median has overlapped where Q1 is. A very interesting data set to talk about would be like if you ask people how many yachts they owned, And the answers were 0, 0, 0, how many yachts you own. So the way that this box plot would look is it would actually be on 0, and that would be the full box plot. So that would be the box plot right there. Not really an informative distribution because of lack of variation, but that would be a box plot completed if all the data points were 0. Now we need to know what is unusual. These are the fences, and I can't say this enough. Fences are a graphical technique that do not remain in your box plot. They are only used to tell you where outliers begin and outliers end. So what we do is we take the IQR, and let's take an IQR right here, and we add it 1.5 times. Notice how that's 1.5 IQRs. Now the lower one would go off the screen if we properly showed it, but notice how we're going 1.5 IQRs above Q3, and then we go 1.5 IQRs below Q1. So to find this out mathematically, write down the formula. Q3 plus 1.5 IQR. So IQR would have to be found for the data set. You're going to have to find that to find the IQR and times it by 1.5. And then you're going to have to take the Q3, which is right here, and add to it. The other formula is Q1 minus 1.5 IQR. And think about this. You're just going where this is at and going below it the same distance. So you go above Q3, 1.5 IQRs, and you go below Q1, 1.5 IQRs. And this is just to tell you where do unusual things begin. You do not keep these fences. They're just a graphical technique. They only tell you where do unusual things begin. You go back to your data now after drawing the fences and find the highest point within the fence and the lowest point within the fence. And this is where the whiskers go to. So notice the gap down here indicates that there are no wind speeds below 0. This is the minimum value. There are no outliers, and nothing can be unusually low. It's not like you walk outside and you're like, whoa, there's no wind today. It's very not windy day, but it's not unusual. It's a little bit lower than we would expect. But sometimes there can be things on windy days that are above what is typical. And that's where the fence is at. But everything within the fence is going to be where we say there's not an outlier. So there's a point in this distribution right here, right up to the fence. There's something very, very close to 5.01. Maybe it's 5. That kind of would make sense. So there's a point that is right near that. What if you go beyond that? Then you're an outlier. Anything outside of the fence is on the low or the high side is an outlier. There can't be low outliers here because there is no negative wind speeds. The wind doesn't go, I don't know how that would work. So there are no negative wind speeds. So with this, you can't have unusually low data points in this data set. It is possible in other data sets, but you can't have unusual low points for this wind data set because there's no logical values that would equate to an outlier on the low side. And once again, we stated many times that things that are outliers are unusual observations. Something that is 1.5 IQRs above usually gets a DWT, and if it's 3, which would be extreme, it would have to be further up than I can draw, it would get a star. So sometimes people use notation to show you something extreme, which would have to be above at least 7.74, and you could calculate 3 IQRs above using the same sort of formula right here, just adding on another 1.5 IQRs to find where the extreme mark would be for an extreme fence. Not all software does that, but if you see a star, it just means extreme outlier. Finally, we're going to remove the fences. We do not leave these fences here. These fences are just a graphical technique to let us know if we are drawing this, where outliers begin or end, and this is our finalized box plot, which could also be displayed in a histogram. Now, I want to point something out with what JMP is doing right here. JMP also gives you this, which is actually the mean, and to be very specific, the diamond itself, which I can't draw today, is a confidence interval for the mean. This would be the lower confidence bound and the upper confidence bound. I believe it's a 95% confidence interval. We haven't talked about any of that stuff yet here, but the confidence interval part, the mean part's the most important. So where the center of that diamond is where the mean is. Notice that the mean is to the right, the median, also indicating a right skew. To review again, when the distribution is skewed to the right, the mean follows the skew, so the mean is higher than the median. So right-skewed data has a higher mean than median. Also, the appropriate measure of center would be median, and the appropriate measure of spread would be the IQR. You can also guesstimate the IQR by tracing downward and looking and saying, it's about 2. Not exactly, but you can guesstimate it and say, oh, how big is that box right there? How big is the box? The box is the range of the IQR. You can also see about where the median is at by telling where the middle line is at. So a lot of information can be obtained from looking at a box plot right here. But once again, one of the key things we love about box plots for comparing distributions is that you can put multiple box plots on a plot. So notice right here, which of these box plots has the greatest range? Can you figure it out? A lot of people will tell me April. In truth, the one with the biggest range is going to be February. Why? This is the min down here. This is the max. Do not forget that outliers drastically increase range. One of our trick questions a lot of times is to show something like this. It's not really a trick question. It's just to make sure you know that outliers are going to drastically impact the range of a box plot. Notice how we see increases to the median. The central tendency of the data is increasing. The central tendency of the data is decreasing and increasing over here. Maybe it has some time order to it. We can see changes to the spread of the data, where the spread of the data is getting about the same. Now it's smaller, and now it increases over here by spread of the IQR. So you can tell a lot from box plots and compare the distributions. Here's how we make side-by-side box plots. It is a bivariate display with a categorical X and a quantitative Y. Remember that we have blue is quantitative and red is categorical. But when it comes to box plots, we can also do a lot more. We can look at the dot plots kind of stacked right there. Not the biggest fan of this. We can add in the box plots, and we can also do a time order for this data if we really wanted right here. So this is kind of a time ordered data set right here, letting us understand some of the differences. Histograms and box plots are pretty similar. Histograms give you a better idea of shape. So if you want to use a graphic that lets you see the shape the best, it's going to be a histogram. Box plots kind of hide some of the features. And then if you have box plots, you can just display a lot of them. So box plots are really good for comparison. That's my biggest tips right there. Side-by-side box plots, really good for comparing things. If you do stacked histograms, make sure they have the same horizontal axis. But imagine if you stack 50 histograms, it's going to be crazy. 50 box plots is still a lot, but much more manageable to look at, especially if you kind of order them by the groups. So box plots look a lot better when you compare groups, where histograms are going to give you a much better idea of what's going on with the shape of the data. Box plots can slightly indicate that, but the histogram is a much better view. Stem and leaf would be better also. Stem and leaves can be problematic because they have so many numbers. So for large data sets, stem and leaves are not your go-to. Stem and leaves are good for small data sets where we want to look at the observations. So how about these outliers right here? Well, we have to usually have some way of handling them, and we want to be careful to not do anything extreme with our outliers. Outliers can be due to special variation. Imagine you're trading stocks and you have a really good day. You make $1 million. Well, I mean, maybe you make $1 million every day, but maybe this is a unique day and you usually make $100. Somehow you make $1 million. You probably want to understand what happened that day you made $1 million. It's probably due to some special cause right there, and maybe you might try to replicate it. So we don't toss out outliers. You don't just toss them out. You try to understand what happened with outliers. Wait a minute, that $1 million was actually $100 and you just moved the decimals around by accident. What about that $1 million? Oh, it was just a fake simulation. We did not understand the question. We made a mistake. Confusion on measurements. The $1 million was actually in Canadian dollars. So what's it worth now? I don't know. Maybe it was worth more. Maybe we lied or made up that number. There's lots of problems that can occur, but sometimes the data is real. Sometimes it has errors. The number one thing you can do is go back to the data when possible and try to correct the data. If that's not possible, we might have to throw away the data. So we try to fix the errors first. We try to figure out what's going on. We never ignore outliers. We take a look at them, understand them, and if we can remove them, because let's say it's an error, let's say someone made a mistake, we will always tell everybody we removed it. We'll mention that there was a data point where we said we made $1 million, but that was actually a typo. We only made $100, and we changed it or removed it. Or let's just say we don't know how much we made that day, so we just removed it because we know we don't have $1 million in our portfolio, and for some reason we can't figure it out, and we couldn't answer the question. And if you can't justify removing the outliers, you can do analysis with and without it, but you need to do analysis with the outliers. So you can do it with and without and say, here's the analysis with the outlier, here's the analysis without the outlier, and show the differences, and then let the readers decide for themselves. You might look at this data from the Kentucky Derby dataset and say, well, wait a minute, there's a ton of outliers. Almost like there's a second mode to this data set. And with that in mind, do we just toss out all those outliers? What's going on with this data set that has a second mode? Well, actually, you have to know the history of the Kentucky Derby. The Kentucky Derby started out much longer. It was 1.5 miles, and that's only from this time frame. We even have an outlier over here where I think that's where it was an extremely muddy race. And then the Kentucky Derby got shorter, and the times, of course, got faster. So now we could compare these distributions. We'd want to put them on the same horizontal axis right here and compare these distributions. And since they have some right skew, the proper measure of center to compare would be median, and the proper measure of spread to compare would be IQR. When comparing two quantitative distributions, you have to acknowledge their shape to figure out what to compare. The second distribution has a much smaller IQR of only 3.4. 125.4 minus 122. Well, it's not that much smaller. The other distribution has an IQR of about 3.25, I believe, 160.625. We'll highlight those numbers as we're talking about them. Minus 157.375. And of course, the longer race has a higher 50th percentile, which is going to be the where 50% or more of the races had their time. The IQR is the range of the middle 50% of the data, is a little bit larger for the longer races. So make sure you know how to understand and compare quantitative distributions. Let me know if you have any questions.